Hello students. In this session, we will continue our discussion of thermodynamics. Okay. During our earlier session, we discussed the first law of thermodynamics. Yes, the different thermodynamic processes we have seen: adiabatic process, isochoric process, isothermic process, isobaric process, and in addition, we also did several numerical problems, right? I recommend you go through that once if you haven't done so already, so that the current session will make more sense to you. Yes? Okay, so let's start with quasi-static process. Okay, well, quasi means almost, or you can say near to. Okay, so what quasi-static signifies? It is near to static or almost static, you can say. So quasi-static process means very nearly static. Yes. Now let me just cite few examples so that you can understand better. Say for example, example 1, expansion of railway tracks in the daytime. Yes, we all know that sun heat causes the metal to expand slowly at a rate such that it can't be seen. Yes, that's why in the railway track you will see a sufficient margin is provided in between two track. Okay, so this process is quite slow, so you can say this as quasi static process. Okay, second example, say growing of our hair or nails. Yes, this process is quite slow. You will see it takes weeks of or 2 weeks 3 weeks to grow your nails or your hair. Yes. Another example, which is the best example, I think that if you are a late riser, getting out of bed in the early morning is a very slow process, isn't it so? So you can say this is quasi-static process. So why I am saying this today is because in today's discussion, we will continue to quasi-static processes only, okay? Whatever topic we are going to learn today, it would be true for quasi-static processes only, okay? Next, we will discuss about heat engine. Okay, so what is it? Basically, it is a device that converts heat energy into mechanical energy. Okay, that means heat energy, or you can say thermal energy, converted into in the form of work. Yes, mechanical energy, it means work, right? Typically, heat engine it consists of three main components. You can say working substance. I am using different color so that you can understand. Source, and final one is sink. Okay. Now what these components are? Well, you can say something like this. A reservoir that supplies energy in the form of heat is called a source, and one that absorbs that energy, this you can call as sink. Okay, this reservoir giving you the heat, so this is source, and this reservoir is absorbing that heat as an energy. You call this as sink. Okay, on the other hand, the working substance, what you called as working substance, let me use black color. So what is this working substance? Well, say it is that entity who absorbs the heat and does the work. Okay, so let's say you can say something like this, that fluid, liquid or gas, any kind of substances, that what we called as fluid, in which energy can be stored or transferred. Okay, all those kind of stuff we can mention as working substances. Okay, so the thing is like this, that the working substance absorbs some heat, say Q1, from the source, and converts a part of it into work, okay? And the rest, Q2, is absorbed by the sink. So from the conservation law of energy, you can say that Q1 equals W plus Q2, okay? Now, since we are talking about engine, the idea of efficiency definitely come, right? Yes, because unless it is an efficient candidate, then it is no meaning to study about it, right? The formula to measure the efficiency, which is commonly known as eta, is defined as in this way. Eta equals, it is the ratio of the net work done by the engine and the total amount of heat absorbed by the working substance. It is absorbed. Okay? Network by the engine, and network means total work. It is not network, okay? It looks like network. It is network means total work. Total work by the engine upon total amount by the heat absorbed by the working substance. The ratio of these two quantity is being measured as the efficiency of a engine, okay? With this formula we can measure the efficiency of the engine. You will get to know about this formula. We will do some problems based on this formula, and you will get the feeling that how the things goes on, okay? So nothing to worry about it. So with the help of this formula, you can also mention this as, in the short form, you can write this eta is the ratio of work done, net work done, W, that is W, and total amount of the heat absorbed by the working substance. Which one is? It is Q1, yes? Because Q1 is the working substance. Yeah. Now, from this equation, we can write this as Q1 minus Q2 upon Q1, right? Simplifying this is have 1 minus Q2 by Q1, yes? So, if you have to measure the percentage of the efficiency, then what we are going to do? We will write this as in this way, 1 minus Q2 upon Q1 times 100. So this will gives us the percentage, how much percentage efficient is. Okay, let me just give you one real world example. Let's say you went to a shop and purchase a pen, okay? Let's say the price of the pen, I mean your buying price is 100 bucks, okay? But is it the real cost of the pen? I mean, definitely the shopkeeper is going to have some profit, right? Unless it is a profit, then he will not sell the pen, okay? So let's say in this 100 bucks, he have the profit of 20 bucks, okay? Yes? So we will say that the efficiency of the shopkeeper is 100 minus 20. Or if you want to say in a percentage, then it is 80%. Now, in real world, you will never find any shopkeeper whose efficiency is 100%. Yes, if the efficiency is 100%, then the shopkeeper would have zero profit, because if the efficiency is 80%, then he have 20 bucks his profit. So if you are making 100% efficiency, unless he is from your family member, okay, so nobody will make 100% efficiency. Any shopkeeper, you will cannot find any shopkeeper in the world who will make 100% efficiency. Similarly, engine also does not have 100% efficiency, okay? So as we have seen, the formula, efficiency measuring formula is 1 minus Q2 upon Q1. Let's mention this as a percentage, okay? So when this will be 100%, if Q2 equals 0, yes. If Q2 equals 0, only then eta will be 100%, which is not possible, yes. Okay, so this one thing you have to understand. I hope it makes sense, yes. And another thing I am going to mention here right now, that this would be required in solving the problems, that in a cyclic process, whenever we have cyclic process, we have delta u equals 0. I have mentioned this in our last session, that u is a state function and what is the cyclic process. But since we are going to solve problems based on this, so I just recapitulate this once again. If you have any doubt in understanding this, I would recommend you once again that go to the last session, the first session of thermodynamics, where I have discussed about this one. Okay, so let's now start doing some numerical problems. Okay, given an ideal gas is taken through a cyclic thermodynamic process through 4 steps. The amounts of heat involved in these steps are Q1, Q2, Q3, and Q4 respectively. The corresponding quantities of work involved are W1, W2, W3, and W4. So the first question is, we have to evaluate W4. And the second one is, what is the efficiency of the cycle? Yes. Now observe that, as I mentioned, it is a cyclic process. Therefore, delta U equal 0. Yes. So from the first law of thermodynamics, Q net equals W net. Yes. Total work done equals total thermal heat. Yes. This implies Q1 plus Q2. We have 4 steps. The thermodynamic process have been carried out through 4 steps: Q1, Q2, Q3, Q4 equals W1, W2, W3, W4. Now we know all of this. In the left hand side, all data are known. On the right hand side, we know W1, W2, W3, and we have to evaluate this one. Yes. So it's pretty simple. W4 implies Q1 plus Q2 plus Q3 plus Q4 minus W1, W2, W3. Correct? W4 equals, now let's just substitute the value. Very simple, isn't it, sir? 5960 plus minus 5585 plus minus 2980 plus 3645. Yes. Minus W1 2200 plus W2 minus 825 plus W3. Yes. So simplifying, we obtain here W4 equals 765 joule. Okay. Now we have to compute the efficiency also. That is eta. As we know, this is net work done upon heat absorbed by the gas. Yes. Because in this case, we have working substances as ideal gas. Yes. Now we have the net work done, which is nothing but, sorry, here we need to have one multiple of 100. Okay, because we are interested in the percentage. Okay. Actually, in the formula in some of the books, you will find this. You will find this. You have to multiply this with 100 just to get it in the form of percentage. Okay. So we have the net work done is W1, W2, W3, W4 upon the heat absorbed by the gas, which is Q1 plus Q4. Yes. Because Q2 and Q3 are negative, it means these are rejected. Okay. So let's now substitute the data from here. 2200 minus 825 minus 1100 plus 765 upon Q1 plus Q4. We have 5960 plus 3645 times 100. Okay. Simplifying, we obtain 1040 upon 9605 times 100. This gives 10.82%. Therefore, the efficiency of the cycle is 10.82%. Yes, and we have also evaluated the total value of W4, which is this one. Okay, I hope it is simple, right? There is nothing so difficult here, isn't it so? So now we will discuss briefly about Carnot engine, which is one of the most important topic in thermodynamics. Okay. Well, it is important in the sense of concept and definitely as well as an exam purpose also. But before diving deeper into the concept of Carnot engine, we need to know first what is a reversible process. Okay. Yes. So now if we observe the definition, so from the definition, you can understand that a reversible process is such that in this case, the system and surroundings can restore to their initial state. So for example, if I is the initial state and F is the final state, then both the system and the surroundings can be restored from each state to another. Yes? From I to F and then from back F to I. Both can restore to each of these state. This is what mean by reversible process. That is, you can go from one position to another position without any change in the universe. This is some sort of cyclic process, right? So giving some simple example, let's say freezing of the water, okay, or boiling of water, or melting of ice, or compression of spring. Yes, all these are reversible process. Yes. On the other hand, anything that cannot go back to the original state, which is not possible, let's say rusting of iron, yes, or cooking of food. Let's say you are preparing chicken tikka, yes. So once you prepare chicken tikka, after that you cannot get back to that original raw chicken, yes. So these are all irreversible process because you cannot get back to the original state, initial position. Apart from that, another important here I want to mention is movement that involve frictional force. Okay, movement that involve frictional force. So this movement is also an irreversible process, which is very important. And in the language of physics, we call this as dissipative effects. Okay, so we will say a process, say P, is reversible if and only if it is quasi-static, as I mentioned in the beginning of today's session, what is quasi-static, and if there are no dissipative effects, okay, that is frictional force kind of thing, okay. Now let us look at one of the famous example. Let's say we have ideal gas here, and we have a piston here, frictionless piston. Now you know that a quasi-static isothermal expansion of an ideal gas inside the cylinder, which is fitted with this frictionless movable piston. So in this case, what is happening basically, since it is an isothermal process, therefore we know that in the case of isothermal process, temperature is constant, right? This implies that this equals 0. Yes, change in energy, it is 0. Yes. So the heat absorbed by the gas equals the work done. Yes. So this is the basic idea that gives rise to the concept of Carnot engine. Okay. I will not go into the details of the concept of Carnot engine, as this session is specially dedicated to focus more on solving numerical problems. But if you want me to do any video on this concept, do let me know in the comment section. Okay. So as we know that thermodynamics is the study of how energy is transformed from one form to another. Yes, basically this is what thermodynamics mean. So when we are talking about heat engines, we are looking how well we can turn energy into useful work. Okay, this is our motivation actually when we are talking about heat engine, like moving a car or generating electricity. Yes. Now, in reality, we all know that it is impossible to make a perfect heat engine in the sense which is 100% efficient. As I mentioned, that you cannot find any shopkeeper who is 100% efficient. Similarly, you cannot find any engine which is 100% efficient. Okay. So, but however, we can figure out what is the highest possible efficiency is for a heat engine that works between two different temperatures. Okay. So if we use a theoretical process, which we will call an idealized reversible process, we can achieve the highest possible efficiency, okay, which in real world engine will always have some kind of irreversibility or loss of energy. Yes, in real world we always have this irreversibility is natural, is practical, which means that their efficiency will be lower than what is mentioned theoretically. Yes. So overall, the concept of Carnot engine is important for engineers and scientists to understand because it helps them to design more efficient engine. Okay, that waste less energy and can do more useful work. It is helpful for them to design more and more efficient engine on the basis of Carnot engine. Now, let me give you some background of Carnot engine in this context, just for your sake of interest. It is a theoretical heat engine that was developed in the early 19th century by a French engineer named Carnot, and till date, it is considered to be the most efficient heat engine possible because it can extract the maximum possible amount of work from a given amount of heat. Okay, which is ideally not possible in real world. Then why it is so important? Well, the reason behind is it is often used, as I mentioned, as a benchmark for comparing the efficiency of other real world heat engine. So if we can figure out that what is the highest possible efficiency for a heat engine that works between two different temperatures, then based on that, engineers can design more efficient heat engines. Yes, that waste less energy and can do more powerful work. Now, Carnot engine works in a cycle of 4 steps. Okay, first step is isothermal expansion. Step 1. Second one is adiabatic expansion. Step 2. Third step, isothermal compression. And the final step is adiabatic compression. Step 4. And the most important part here that I am going to discuss right now is Q1, Q2, T1, T2, this tuple. Okay. So what they basically represent is the heat absorbed. Let me just write down here. In step 1, what is happening? Since it is an isothermal expansion, the working substance or fluid or gas absorbs heat Q1 from a high temperature reservoir at temperature T1, okay, which is used as to do work done W1 to the surroundings, okay. And in step 3, what is happening? The same working substance, fluids or gas, whatever, releases heat Q2 to a low temperature reservoir at temperature T2, and this heat is also used to do work W3 on the surroundings, okay. After doing some computations, you can show this that this ratio is equal, which is the specialty of Carnot engine actually. And in this case, therefore, you can prove that eta equals 1 minus T2 upon T1. Yes? Therefore, the efficiency of the cycle is this. And as I mentioned, it is an ideal engine and has lots of theoretical importance, but practically it is not possible. Okay, so now with the help of this formula, this one and this one, we will solve some numerical problems, okay? Given a Carnot engine takes 1000 kilocalories of heat from a reservoir at 827 degrees Celsius and exhausts it to a sink at 27 degrees Celsius. How much work does it perform? What is the efficiency of the engine? Now observe that 827 degrees Celsius, this one is the source, right? Yes? Source is 827 degrees Celsius because it takes, yes, and it exhausts. That means it rejects 27 degrees Celsius. Therefore, 27 degrees Celsius is the sink. Yes. So this one is T1 and this one is our T2. Okay. How much work does it perform? What is the efficiency of the engine? Now, as I mentioned earlier, that in case of Carnot engine, we have eta equals 1 minus T2 upon T1, right? So from here, since we know T2 and T1, we can easily compute eta, right? Sorry, it will be multiplies 100, okay? So from here, we can easily compute eta, yes? Also, we have to calculate the work done it performed. But I want to alert you here that you need to convert this into Kelvin, okay? So T1 equals 827 plus 273. This gives us 1100 Kelvin, and T2 equals 27 plus 273, and this gives us 300 Kelvin. Now if we substitute the value here, I am using different color. 1 minus T2 300 by T1 1100 times 100, 1 minus 3 upon 11 times 100. This gives 11 minus 3 upon 11 times 100, 800 by 11, which if we simplify, it is almost 72.72%, okay? So this is the efficiency of the cycle, yes? Now we have to, so we have finished this one, second part is finished. Now we have to determine how much work does it perform. It is also pretty simple, as we have seen, the W given by this formula, Q1 minus Q2, yes? We know Q1, yes, because 1000 kilocalories of a heat. This one is our Q1, right? So how much is Q1? 1000 kilocalories means 10 to the power 6 calorie, right? Yes. We have to determine Q2. How we can determine Q2? It is also pretty simple. Q1 by Q2, as we know, this one equals T1 by T2. Yes. So we'll just substitute the value and we are done. Very simple, isn't it so? Q2 equals Q1 times T2 upon T1, right? So if we simplify this, we have our Q1 10 to the power 6 times our T2 is 300 and our T1 is 1100. Let's simplify this. We have, it is almost 2.72 times 10 to the power 5 calorie. So from here we obtain our Q2, right? We know Q1, we know Q2, therefore we'll just substitute the value here and we are done. 10 to the power 6 minus 2.72 times 10 to the power 5, which you simplify, we obtain this as 7.28 times 10 to the power minus 5 calorie. Okay. Yes, see, it is so simple. You just have to substitute the value into the formula, that's all. Calculate the least amount of work that must be done to freeze 1 gram of water at 0 degrees Celsius by means of a refrigerator. Temperature of surroundings is 27 degrees Celsius. How much heat is passed on the surroundings in this process? Latent heat given as 80 calorie per gram. Now, you know, an ideal refrigerator, you can consider it as a Carnot type cycle in a reverse process, okay? It is a reverse Carnot cycle, okay? So let me just tell you one thing, that whenever you are solving problems, numerical problems in physics, mathematics or chemistry, everywhere, your first duty should be to note down the data you have in hand, okay? So in this case, what are the data you have in your hand? You know L, you know the latent heat, you know T1, you know T2. So your first duty should be to write it down. So you have T2 equals 0 degrees Celsius, which we convert it into Kelvin, we obtain 273 degree Kelvin. Yes. We have our T1 27 plus 273 equals 300 Kelvin. Yes. And we have latent heat equals 80 and our one, and we have 1 gram of water. Therefore, Q2 we have the formula ml equals 1 times 80 equals 80 calorie, right? Do you have any doubts here? Yes? Till now everything is fine, okay? So now what we have to determine? We have to determine Q1. It is also pretty simple, isn't it so? We will apply the same formula. Q1 by Q2 equals T1 by T2. If we simplify here, Q1 equals T1 by T2 times Q2. Yes? We have our T1 300, our T2 273 times. If you have any doubts, do let me know in the comment section, okay? I will make you understand this. So it is, if you simplify this, it is almost 87.91 calorie, okay? Okay. So how much heat is passed? This one, yes? Okay. Given a Carnot engine having an efficiency of 1 by 10 is being used as a refrigerator, if the work done on the refrigerator is 10 joule, then the amount of heat absorbed from the reservoir at lower temperature is. Now, as I mentioned, note down the data first, whatever you have in your hand. You have eta equals 1 upon 10, yes? You have work done equals 10 joule, yes? What you have to determine? You have to determine the amount of heat, that is, you have to determine Q, yes? And we know the relation between Q, W, eta. But here there is a catch. And the catch is, I mean, it is just an important formula you have to know beforehand solving this type of problem. Whenever you have problem with refrigerator, the coefficient of performance of refrigerator, which is mentioned as beta. Let me just write it down here. The coefficient of performance of refrigerator, which is mentioned as beta, and the relation between beta and eta is something like this. Beta equals 1 upon eta minus 1. Okay, and rest everything is same. Beta equals, and once you evaluate beta, beta equals heat extracted from the cold reservoir upon work done. Okay, so that is beta equals this Q upon W. Yeah, since we know beta is this quantity, so 1 upon eta minus 1 equals Q upon W. We know W equals 10. Finish. We just have to evaluate the value now. That's all. So 1 upon eta is 10 because eta equals 1 by 10. So it is 10 minus 1 equals Q by 10. And from here we obtain Q equals 10 times 10 minus 1, 9. So here we have 90 joule. Yes. Given in changing the state of a gas adiabatically from an equilibrium state A to another equilibrium state B, an amount of work equal to 22.3 joule is done on the system. If the gas is taken from state A to B via a process in which the net heat absorbed by the system is 9.35 calorie, how much is the net work done by the system in the latter case? It's a bit subjective type question, but nothing to worry, it's pretty simple to solve. First, observe the line, the underline I have mentioned, it is done, the work done is done on the system. Therefore, our W will be negative, okay? Because work is done on the system, okay? So we can write W as minus of 22.3 joule, okay? Now, since this is an adiabatic process, therefore, Q will be 0. Let me just write it in a same alignment so that you can understand. And this is our first, this one. I am solving first this one, okay? Process 1. Let's name this as process 1. So we have Q equals 0 because we are in the adiabatic process. And we know that from the first law of thermodynamics that delta U equals Q minus W, and since Q equals 0, so it was minus, so it is, and since Q equals 0, so it is minus of W, implies delta U equals minus of, therefore delta U equals minus of 22.3, therefore 22.3 joule. So we obtain our internal energy as 22.3 joule, okay? Now, for another process, let us now look at this one. We have, I am using different color. Let's use blue color. So let's mention this as process 2. Okay. So in this case, what is happening? The gas is taken from state A to B. Observe that the initial and final position remains same. Yes. Initial position, final position, final position. So since the initial and final positions are same, therefore, this quantity will remain same, right? As I mentioned in our earlier classes that internal energy depends only on the initial and final position. Okay. So delta U will remain same. Delta U is same. And in this case, the heat absorbed Q is 9.35 calorie. But we need to convert this into joule. Therefore, we are going to multiply it with 4.19 and we obtain it as 39.18 joule. Okay. So our heat absorbed is 39.18 joule, okay? And since delta U is same, therefore we are going to use the same formula, this one. Delta U equals Q minus W implies W equals Q minus delta U. Pretty simple, isn't it, sir? You just have to remind the formula, that's all. The problem will be finished. As I said in the earlier classes, that you just have to know the formula, that's all. Simplifying, what you are obtaining? We are obtaining 318, it is 16.88 joule, okay? Almost you can say 16.9. Okay, so D is the final answer, okay? So simple, isn't it, sir? You just have to remind the formula, that's all. Refrigerator works between temperature of melting ice and room temperatures. The amount of energy in this unit, kilowatt, must be supplied to freeze 1 kg of water at 0 degrees Celsius. So observe that we have the data what is given here. Let's first note it down. Temperature of melting ice, that is 0 degrees Celsius. Since it is the temperature of melting ice, that is, it is absorbing the heat, right? So it is sink. Therefore, this is our T2 and this is our source temperature, room temperature, 17 degrees Celsius. So we need to convert this into Kelvin. And this one converting to Kelvin. Okay. Now we know that coefficient of the performance of a refrigerator, as I mentioned in our last problem, it is given by Q2 by W equals, which is our beta, right? Implies, and we can write this, and we can write this as T2 by T1 minus T2, correct? This implies, now observe that we have our Q2 is mL, right? Where L is the latent heat and mass is given as 1, so it is 1000 gram times latent heat 80 gram, and we need to convert this into joule. Therefore 80 times 4.2, yes. So substituting the value, 1000 times 80 times 4.2 upon W, this equals 273, 290 minus 273. I hope you guys understand this, that how it is. Yes, it is simple. It comes directly from the formula. Let me just write it down here so that you can understand. We know that Q1 by Q2 equals T1 by T2, right? Therefore, Q1 by Q1 minus Q2, we can write this as in this way. And we know that W equals Q1 minus Q2. Yes, so also the formula is here Q2 by W, therefore we just replace Q1 by Q2 in this way, okay? So it is simple. Now if we simplify here, we obtain W as 1000 times 80 times 4.2 multiplied by this 290 minus 273. This is 17 upon 273. If we simplify this, we obtain, this is equal almost 20923. Now we need to convert this into kilowatt hours, right? We need to convert this into kilowatt hours, and we know that 1 kilowatt hour equals 3.6 10 to the power 6 joule, okay? So you have to divide this with this one. Therefore, because the answer is in this unit, yes. So the work done in this unit, work done in Joule, sorry, work done in kilowatt unit will be 20923 3.6 10 to the power 6. So it is 0.058. Therefore, C is the correct choice. Okay. Given a Carnot's engine working between 400 Kelvin and 800 Kelvin has a work output of 1200 joule per cycle, the amount of heat energy supplied to the engine from the source in each cycle is. Okay, so what are the data we have in our hand right now? We have it's working between 400 and 800, right? So we have our T2, let me just write it here, answer. So we have our T2 is 400 Kelvin because it is absorbing heat, and our source is 800, and we have the work done 1200 joule. Okay, we have to determine the, yes. So as we know, the formula for Carnot engine, T2 by T1 equals Q2 by Q1, but we don't know Q2, so we will remove Q2. Okay, how we can remove? Simple, by the formula. Yes, observe that all the cases we are just doing the arrangement of formula. Okay, so as I mentioned always that you just have to remember the formula, that's all. The problem will be get solved automatically. 400, 800, now we have our Q1 and W 1200 by Q1. Okay, now if we simplify this, this is half. If we simplify this, 1 minus 1200 by Q1. So from here we obtain 1200, simplifying this equal half. Therefore from here we obtain our Q1 as 2400 joule. Yes. So D is the correct choice. Given 1 mole of a monoatomic ideal gas is taken through the cycle shown in figure, A to B adiabatic expansion, B to C cooling at constant volume, C to D adiabatic compression, and D to A heating at a constant volume. The pressure and temperature at A, B, etc. are denoted by PA, TA in this way. And given the initial data, temperature at this point is 1000 Kelvin, PB, PC, the relationship, and we have to solve by calculating the work done by the gas in the process A to B and the heat lost by the gas in the process B to C. And some constants values are given here. Okay, so before working out on this problem, I just want to give some piece of advice that I have seen that it is very common for students to get scared. They often get scared when they see this type of subjective questions. It is often the case that they lack self-confidence and believe that they cannot solve the problem. Okay. Therefore, I would strongly advise you in this case that you should avoid this type of negative thinking, okay, so that you can keep focused on finding the solution. Yes? Okay, so let's now see how to work out this problem. So first, we have to calculate the work done in the process A to B. Yes? Now observe that it is given from A to B, the process is adiabatic expansion, right? And we know that in case of adiabatic expansion, the work done is given by this formula, yes, in R delta T by 1 minus gamma, of which we know the value of N. Let me use different color. We know N, yes, because it is given monoatomic. We know R is constant, value is given. We know gamma because it is a monoatomic ideal gas, and in this case we know the value of gamma is 5/3, yes. So the we have to investigate about this delta T, yes. So what is delta T? Delta T is basically T final minus T initial, and in this case I think it would be TB minus TA, of which we also know TA, right? TA is given, so we have to evaluate TB only. That's all. Finish. See, so simple. We just have to evaluate TB. That's all. So if we can evaluate TB, then we can solve this. Yes. Okay. So how to evaluate TB? Okay. Now, since this is an adiabatic expansion, we know that PV gamma equals constant, right? Yes. But in this case, we do not have any T terms here, right? There is no terms of temperature here, right? So what we are going to do, we will evaluate V, okay? Since by using this relationship, okay? Using this relationship, we will evaluate V. So from here and here, we obtain V equals nRT by P, yes? nRT by P. See, now we have a T term here, okay? This implies, now since we have monoatomic gas, therefore our N equals 1, right? So simplifying, we obtain in this case R T gamma P gamma, and we have P here. This is constant. I am writing it as C, okay? I am writing constant as C, yes? This gives us P1 minus gamma, and since R is also a constant, so we can write this in this way. Constant, say C naught, okay? C naught is also a constant because R gamma both are constant. Now, since we have left hand side, this is known terms, but we do not know anything about C naught, right? C naught is constant, there is no question about that, but we do not know the value of C naught. So with this equation, it is not possible for us to evaluate T, right? We need T, yes? So what we are going to do now, we will do this technique. Since this is constant, therefore PA1 minus gamma T gamma equals PB1 minus gamma, sorry, it would be TA. Yes, throughout this process, this relationship will hold, right? At PA, TA, PB, TB. Okay, so now from here we can easily evaluate TB, right? This implies our TB gamma equals PA1 minus gamma TA gamma by PB1 minus gamma. Yes. Now, what are the values known here? We have given PB and PA the relationship which is easily obtained from here. If we simplify this, yes, I don't think there would be any doubt here, right? We know PA, from here what we are obtaining. We have PB by PA equals 2/3. Therefore, PA by PB would be the reciprocal of this one. Therefore, it would be 3/2. Yes, 3/2, 1 minus gamma. And TA is given 1000. Yes, 1000 gamma. From here, we obtain our TB 3/2, 1 minus gamma upon gamma by, sorry, times 1000, okay? Yes, now see, we right hand side, look at the right hand side. There is no unknown terms here. So if we now substitute the value of gamma, 3 by 2, 1 minus 5 by 3 upon 5 by 3 times 1000, right? This equals, so now I am doing some basic simplification. There is nothing so difficult here. Yes. So now if we simplify this, 2 by 3, 2 by 5. Now 2 by 5 is 0.4, right? This you can write 0.4, and the value of this one is given as 0.85. So 0.85 times 1000, this is 850, okay? So we obtain our TB as 850 Kelvin, right? See, I have written the equation somewhere here. Yes. So we obtain TB from here and we know TA. So now we are going to just substitute the value. That's all. Yes. So let's go to the next page. Our work done, W equals NR delta T upon 1 minus gamma. We have the N, our is 1. The value of R, how much it is given? It is given 8.31 joule. Yes. 8.31, and this is our TB minus TA, and this is our 1 minus 5 by 3. We just have to simplify here, that's all. We have our TB as 850, this is 1000, this is minus 2 by 3. Now if we simplify this, by simplifying we obtain it is 1869.75. So the work done is, yeah, I am writing this as AB because the process is from A to B, right? So it is AB. So the work done is this one, okay? But we have another part of this problem, problem B. So we have to calculate the heat lost by the gas in the process B to C. So you have to calculate the heat lost. It means you have to compute these terms, right? Let me use different color. We have to compute delta Q, right? Because this is a heat loss. So how you can do this? Can you guess? Think for a few minutes. Pause the video, think for a few minutes how we can solve it. Okay? Actually, what we are going to do now, see, from B to C, we have volume is constant, right? And we have to evaluate delta Q. Yes? So basically, what we have to do now, we need to apply first law of thermodynamics. Yes? Yep. Simple, very simple. Isn't it so? Because V is constant, in this case, from B to C, it implies that delta W will be 0, right? So, delta Q equals delta U. Yes? Now the question is, from here, how we can proceed? Well, you know, there are two methods basically of finding delta Q, okay? And one of these that we are going to apply here is, we know that delta U, we know that for change in internal energy of the gas, in that case, delta U equals N CV delta T, isn't it so? Where CV is the specific heat of the gas for constant volume, right? You know this relationship, right? Cp minus Cv equals R. Yes? So we are going to use this Cv, that is specific heat of the gas at constant volume, okay? And we also know that Cv equals 3 by 2 R. Yes? So we are going to apply this two relationship. This one is not required for the time being, but it is an important relationship to remember. Okay, so we are going to use this relationship here. So we have delta U equals N 3 by 2 R delta T, right? Yes? Now if we simplify this, we have, since our n equals 1, 1 times 3 by 2 R times Tc, since we are going from B to C, Tc minus Tb, right? This implies delta K equals 3 by 2R. Now we do not know anything about Tc, so let's just keep it as it is, and we know Tb, right? We have evaluated our Tb as 850, okay? So 850. Now, how can we evaluate this, the right hand side, as we do not know Tc for the time being, yes? But we know one thing, that V is constant throughout this process. Since V is constant throughout this process, therefore we can write this in this way. So similarly, if you observe that what we did last time, we took the ratio, right? Because in this time, we do not know about V, so we evaluate V, right? And we put it into the ratio form, right? So we are going to do the same kind of thing here also. Since we do not know about Tc, so since V is constant in this case, so we are going to use this relationship, that P varies with T, and this gives us Pc by Pb equals Tc by Tb, right? From this relationship, and from here we can evaluate Tc, yes? So what is our Pc? The relationship between Pc and Pb is given here. It is Pc equals 1 by third Pa and Pb equals 2 by third Pa. So let's just put this to value. It is 1/3 Pa by 2/3 Pa, right? This equals Tc, and we know our Tb as 850. So let's just simplify this. From here we obtain half of 850, which is 425. Therefore, our Tc we obtain as 425. Yes? So now we will straightforward substitute the value here. Delta Q 3 by 2R 425 minus 850. Did you observe one thing? This would be a negative. And in the question C, it has mentioned the heat lost. Yes? So C, our answer is correct in the sense, even if we do not simplify the answer yet, but still we are sure that our answer is correct, because our answer is coming in the negative terms. And it would be, yes, because we have loss of heat, right? Therefore, from here, by substituting the value of R, if we now simplify this, 3 by 2 times 8.31, 425 minus 850, it is 425, right? Because it is half of. So if we simplify this, we obtain minus 5297.625 joule. Okay. So this much amount of heat has been lost, yes, by the system. Yeah. Okay. So if you have any doubts, do let me know in the comment section. Okay.